Good evening, one and all. Is my screen visible? Am I audible? Okay. Shall I start the class? Let me record the video. Record it. Okay. In the last class, we have seen how to construct a common bus system and how this common bus system is used for communication between the register. How to transfer the data between the registers and memory. All that we have seen using how to transfer the data between registers and memory using a bus system we have seen in the previous class. Now we'll see what are the different type of computer instructions we have. Different types of instruction. Whenever you want to design a computer, for designing of a computer, you require different computer instructions. What are those? In our computer system, mainly there are three categories of instructions: memory reference instruction, register reference instruction, and input output instructions. These are the main three categories of instructions we have in our computer system. First, we'll see memory reference instruction. What do you mean by memory instructions? Whenever you want to execute any instruction, the required operands, if you are fetching from the main memory, then we'll call those type of instructions as memory reference instructions. Generally, how you will execute the instruction? First, you will retrieve the data or the instructions from the main memory that will be stored in the accumulator. After that, the execution process will start. And if the required data or the required operand values, if you are fetching from the main memory, then we will call it as a memory reference instruction. You are referring the main memory to execute the instructions. That is memory reference instruction. Right? You already know the format of an instruction. How many bits are given for instruction? Total 16 bits from 0 to 15. In the last class, I explained the format of the instruction. So, instruction register size is of 16 bits. And this instruction is mainly divided into two parts. First part is your address part. How many bits are given for address part? Number of bits given for address. Yes, 12 bits are given for address part. And remaining 0 to 11 are given for address. The second part is your opcode. Actually, the second part from 12 to 15, it is your opcode. Again, that opcode is divided into two parts. 12 to 14 bits is your actual opcode. The operation code specifies the operation code, and 15th bit specifies the type of the address, right? So here, when you see this format, so by changing the values of this opcode, you will get different memory reference instruction. Then by changing this opcode value, that is the bits from 12 to 14 bits. If you change the value of 12 to 14 bits, Then you will get different memory reference instruction. Now I'll tell you what are those different memory reference instruction, right? Initially, so your 15th bit is 0. Next, if the remaining bits 12 to 14 bits are 0, 0, 0. If the bits, opcode bits are 0, 0, 0. Now, what is the corresponding decimal value for this? It is 0, right? So, 0 and this part always specifies the address. For what this address is used? Perform this particular operation. To perform this operation, what from where you are supposed to retrieve the data from the main memory. That address is specified in this location, right? In these 12 bits, from where you have to retrieve the data, that address will be specified. So 0, that address is not known now. That address can be anything based on the requirement of the instruction, right? So 0, XXX is something like address. That can be anything. So this code designates which operation? So this code 0th x designates AND operation. AND operation. What you are ANDing? On which data you are performing the AND operation, right? So here, using this address, you will fetch the data from the main memory, right? That data is to be ANDed accumulator. Whenever the opcode values are 0, 0, 0, then AND operation is performed on the data fetched from the main memory with the data present in the accumulator. Clear? Next, if you change the opcode value as 0, 0, 1, then the hexadecimal code given for this is 1. The corresponding decimal value for this is 1, right? So the code given is 1 and the address can be anything. Then what this code will do? What this code will do? This code will perform add operation on which data? Add operation is performed on the data fetched from the main memory with the data present in the accumulator, right? On this data, add operation is performed if the opcode value is 0, 0, 1. Next, if the opcode value is 0, 1, 0, if the opcode value is 0, 1, 0, then the code designated is 2 followed by an address, right? Now, what this operation will do? This operation will load the content of the main memory into the accumulator. Using this address, you can locate the main memory, right? Whatever the data is present in this address is fetched and that will be loaded into your accumulator if the operation code is 0, 1, 0. Next, 0, 1, 1. If the operation code is this, then what the code given for this is 3 followed by an address field, right? Then what this will do? This operation, what it will do? It will store the content of the accumulator into the memory. If the address is something like 100, then if your accumulator is having some data something like 1001 so on, that data will be moved to the location 100. That is the meaning of the code STA. And so here AND means it performs AND operation. Add means performs addition operation. LDA means it loads the content into the accumulator. STA means storing the content into the main memory. Storing the content of accumulator into the main memory. Next, if the operation code is 1, 0, 0. If the operation code is 1, 0, 0, then the code given is 4 followed by an address. Then what this will do? The operation performed to be BUN. What is the operation to be performed? It is BUN. BUN means branch unconditionally. Branch unconditionally. What does it mean? Generally, your program will have a sequence of instructions to be executed. That means a particular sequence will be followed to execute that instruction, first instruction. Then after first you have to execute second. After second you have to execute third. Like that, the sequence will be there. But whenever you want to jump from the current instruction to another instruction which is not there in the sequence, then in that case you can use the instruction BUN. In that case you can, that means to change the sequence from first instruction, if I want to directly go to the 10th instruction, that means your instruction is branched unconditionally to the next instruction which is not there in the sequence. Next, if the opcode value is 101, then the hexadecimal code given is 5 followed by an address. What it will do? The code, the operation performed is BSA, branch and save the return address. Branch and save the return address. This is similar to your branch instruction only, but the return address from where you are branching, that address will be stored. In case of branch unconditionally, you can jump from one instruction to the another instruction which is not there in the sequence. In case of branch and save return address, you are jumping from one instruction to the another instruction, and when you are coming back from that instruction, you are storing that return address from where you are returning. That is what BSA instruction is. And the last one is 110. 110. The code given for this is 6. Code means nothing but the corresponding decimal value. What is the corresponding decimal value for 110? 2 power 0 into 0, it is 0. 2 power 1 into 1, it is 2. 2 power 2 into 1, it is 4. 4 plus 1 is 4. 4 plus 2 is 6. So the code given is 6 followed by an address. Right? What this will do? ISZ, increment and skip if 0. That means increment the content of the accumulator, and after performing the increment operation, if the accumulator content becomes 0, then you need to skip the next instruction which is in the sequence. Right? If you are executing the second instruction, at that time, if you perform an increment operation on accumulator, then if accumulator becomes 0, you should skip the next instruction. What is the next instruction? Third instruction. Skip the next instruction because accumulator is 0. That is ISZ. Right? Now, when you observe this opcode, ith bit as well as your opcode, here how many addresses we got? How many different instruction, memory reference instructions we got? 7 memory instructions, right? So in these 7 memory instructions, the ith bit value is 0, which indicates that this address is a direct address. That means in this location, you will have the operand value, right? So whenever you change this in ith bit value to 1, if you change the ith bit value to 1, and if your opcode values are like something like 1000, then the code given is 8XXX, 8 followed by an address field. Then what it will do? It will perform the same AND operation only. But only difference is here this address is not a direct address. This address contains the address of the address where the actual operand is present. In the same way, if the opcode is 001 with the 15th ith bit value as 1, what this will do? The code given is 9 followed by address field, and the operation to be performed is add operation. Next, if you change it to 010, then it will be 10 actually. So when you represent hexadecimal code in hexadecimal code, then it will become A followed by an X field. What it will do? It will load the memory content into the accumulator. Right? So these operations were same. Only difference is if I value is 0, here this your address field contains the actual operand. Whenever I value becomes 1, these operations were same. Only difference is this address is not a direct address. It contains the address of the address, right? So these are the different memory reference instructions. Next, move on to register reference instructions. So, in case of memory reference instruction, from where you are fetching the data, from where you are fetching the operand values, from the main memory. In case of register reference instructions, we are executing the instructions on by using the data stored in the registers. So the instruction execution is depending on the data stored in the register. In case of memory reference instructions, the address field is common for all the instruction, right? So here this address field is not changed. Only by changing this opcode value you are getting different memory reference instruction, right? But in case of register reference instruction, this opcode value is fixed. The bits from 12 to 15 are fixed by changing the bits from 0 to 11. That is, by changing this address field, you will get different register reference instruction. And what is this fixed value? The opcode value? The opcode value is 111 and this ith bit should be 0. Total these 12 to 14 bits, 12 to 15 bits are 0 followed by 3 ones, and this is fixed. Only by changing these 12 bits, they will get different operation. Now we will see what are those different register operations, right? So I already told you that 0, 111, it is fixed. This opcode is fixed. Now in these 12 bits, if the 12 bits are 1, 0, 0, so on. 11th bit is 1 and remaining all bits are 0. Now what is the code, hexadecimal code for this? So consider 4 bits ma. 0, 111. The code for 0, 111 is 7. Next 1, 4 zeros. 1 3 zeros. The code given for 1 3 zeros, the decimal code is 8. So 7 8 remaining are zeros only, right? So the hexadecimal code for this instruction is 7800. Now if your instruction is 78 is having a code of 7800, what it will do? It will perform CLA. CLA. What does it mean? Clear the content of the accumulator. Whatever may be the content present in accumulator, you made it to 0. That is the meaning of CLA instruction. Next, if the register, if this address, if these 12 bits are something like this, 0 111 is fixed ma. So the code is 7 only. Next, I have changed this 10 to 01. Then what is the corresponding code? 7 4. This is 4. Next 0 0. Take 4 bits. So the hexadecimal code is 7400. So if this instruction value is 7400, the code is 7400, what type of instruction is executed? CLE. Clear the content of E. Can anyone tell me what is this E? In the last class I explained what is E. Can anyone tell me what this E means? Yes, extra bit, right? So at the time of common bus system, I explained you have an arithmetic logic unit. From there you will get the output, right? So along with that you will get an extra bit. When you will get this extra bit, when you are performing addition operation, you may get carry. When you are performing subtraction operation, you may require borrow value. So all those values will be stored in the extra bit, right? So clear the content of that E flip-flop. That is what the meaning of 7400. Next, if the code is this one. If you change this 0 to 12 bits as 0, then the hexadecimal code for this is always 7 ma. 0 111 is always 7. Next 0010 value is 2. Next 0 0. So the hexadecimal code for this instruction is 7200. Then what type of operation is performed? CMA. CMA means complement the content of the accumulator. You know what do you mean by complement, right? Make 1 as 0, make 0 into 1. So complement the content of the accumulator. Next, if I change the values to like this, 0 triple 1 followed by 3 zeros 1 followed by all zeros, then the hexadecimal code will be, it is 0. This way is 1 followed by zeros, 7 1 double 0. Then what operation you have to perform? Complement the content of E flip-flop. Complement the data present in extra bit. Right? Next, if I change it to like this, the code this is 7, now it is 0. The next 4 bit values are 8, 7080. So 7080. What it will do? CIR. Perform circular shift right on AC, that is your accumulator, as well as on your E flip-flop. You know what is a circular shift right? Circular shift right means what? Move the contents of the register 1 bit to the right side in a circular manner so that no data is lost. LSB becomes MSB, MSB becomes LSB. Right? Circular right is to be applied. Next, if it is like this, right? 7 0. Now what is this value? 4 4 0, 7040. Then perform CIL. Apply circular shift left on AC as well as E. CIR means circular right shift. CIL means circular left shift. Next, if the code is this, if the code is, if I change the code to, then the value hexadecimal code becomes 7 0 and this is 2 and 0, 7020. What you have to do? INC, increment the content of AC. Whenever I say increment, always increment should be +1. Decrement is -1. +1, add 1 to the content of the accumulator. Next, change it to this. If the code becomes like this, if the instruction is having data like this, then the corresponding code will be 7 0 0 and this is 8. Right? Then it becomes SPA. What do you mean by SPA? Skip the next instruction if AC is positive. That is, if the content of the accumulator is positive. How or not? Here I said you need to skip the next instruction in the sequence, right? By using the, yes, very good, by using the MSB bit. If the MSB bit is 0, it represents a positive. If it is 1, it represents a negative value, right? Skip the next instruction if MSB bit is 0 in the accumulator. Next, change it to one second, sorry. Next, if the code becomes like this, then the corresponding hexadecimal code will be 7008. What you have to do? Skip the SNA, skip the next instruction if AC is negative, right? Next, the code becomes like this. The corresponding hexadecimal code will be 7004. What you have to do? SJDA. Skip the next instruction if the content of accumulator is 0. If AC is 0, skip the next instruction. Next, if the instruction is like this, then the corresponding code is 7002. Next, what you have to do? Skip the next instruction if E is 0. If E is 0. And the last one is, the code is 7001 and the operation to be performed is HLT. Halt the computer. Nothing will be performed. Clear? So these are different register reference instruction. You will get these reference register instruction by changing the bits from 0 to 12 bits. By changing 0 to 11 bits, then you will get different values. But the opcode value will be same. 0. Ith bit value is 0 for register reference instruction. And your opcode value is 111. Clear? Now go to the next one. What is the next instruction? Input output. Third category of instructions is input output instruction. Right? So these input output instructions are mainly used for communication with the input devices as well as the output devices. To get the data from input devices, to produce the data onto the output devices, you require input output instructions, right? Same as register reference instruction, in your input output instructions also, different operations, different instructions you will get just by changing the value of 0 to 11 bits. By changing 0 to 11 bits of your instruction, you will get different IO instruction. In case of register reference, the opcode is 111. Here also the opcode value is 11 only, but difference that is your to 1 in case of IO instruction. If it is 0 for register reference instruction and here it is 1 for IO instruction. Let us see the different types of IO instruction, right? So this is your instruction format, and in these instruction, in these 16 bits, these 4 bits are fixed. 15th bit is 1 and 12 to 14 bits. Your opcode bit values are 4, 1. Now, if it is this one, if the data is like this, 1 followed by all zeros, then the corresponding hexadecimal code is, for this 1111, the hexadecimal code is F. For 1000, the code is 8. And for this, the code is 00. So, F800 is the code given. What this will do? It will perform INP instruction. What do you mean by INP? Input the character to the accumulator. Input the character to the accumulator. That input data, it is stored in which register? In which register the data coming from the input device is stored? In which register input data is stored? In the last class I explained. INPR, input register. Input register holds the input characters, right? So from there, from INPR, if the code is F800, the data or the input character is moved to your accumulator. If the code is F800. Next, if the code is this, if the code is this, F, this is 4 and these are 0, F400. What does it mean? OUT instruction. Output the character from the accumulator. Output the character from the accumulator. That is, whatever is present in your accumulator, you just send it to your output device. To send the data onto the output device, which register is responsible? Which data will hold the output character, whatever you want to display on the output device. To get the input data, INPR is used. In the same way, to send the data onto the output device, outer register, OUTR, outer register is used. Can anyone tell me what is the size of INPR and OUTR register? Size of INPR and OUTR, outer and input register. Yes, 8 bits. Okay? Okay, very good. Next, change it to like this. Next, if the code is F200, then instruction to be performed is SKI. Skip the next instruction if the input flag is on. We'll discuss this input flag, output flag, if these interrupts in the next sessions. In further sessions, we'll discuss. Right? So, if this code is F2 instruction in the sequence, if the input flag is on. In the same way, if it is F100, then skip the next instruction on the output flag. It is SKO. Right? Next, the code is F080. Then Interrupt is on. Interrupt is enabled. The instruction is ION. And the last instruction is, and the last one is, the code given for this is F040. Interrupt is off. Interrupt enabled off. IOF. We'll discuss about interrupts and input flag, output flag. I'll tell you in the further unit. So these are the different IO instructions. 25 different types of instructions were there. Memory reference, IO instructions, register reference. When you combine all the three, they present total of 25 instructions. Now, my question is, when we say that the instruction set is complete, whenever instruction set is complete means we have all in these 25 registers, all types of registers were present. Sorry, all type of instructions were present. What are those all type of instruction? Means what are the different category or different type of instructions should be there in your system for your system to work properly? They are, so instruction set completeness. Completeness means what are the different types of instructions you should have to have a complete set of instruction, right? They are logic and shift instruction. Check whether you have this arithmetic, logic and shift instruction in those 25 instructions. Till now we have discussed three categories, right? How many different instructions we have in those three categories? Total of 25. So in those 25 instructions, whatever I am telling now, if you have all these categories of instructions, then we can say that your instruction set is complete. That means all types were there in your system. Right? So first category should be, it should contain arithmetic instruction. You have an add instruction which comes under arithmetic instruction, right? Logical instruction. In memory instructions, in memory reference instructions, you have AND operation which comes under your logical instruction. Next, shift instruction. In register reference instruction, you have shift, circular shift instruction, right? So if you have all these three categories of instruction, then you can say that that is one of the condition for your instruction set to become complete. First condition is satisfied. Now see the second one. Instructions, you should have instruction to move the data from memory to the accumulator as well as from accumulator to the memory. Do we have the instructions for that? Do we have the instructions for transferring the data between memory and the accumulator? Yes, you have. In the memory reference instructions only we have. Load the accumulator with the content of the memory. LDA is load the accumulator. Similarly, STA means store the content of the accumulator into the main memory. Right? Yes, you have these instructions. You have instructions for moving the data between memory and accumulator. Second condition is also satisfied. Next, third condition is program control instruction. That means your program will have certain instruction. Program is always a set of instructions to be executed. Means you have a sequence of instructions to be executed. 1, 2, 3, so on, like that. A sequence is there. Middle of the program, if required, you should have instructions to change the sequence. That means to jump from one instruction to the another instruction, you should have instructions, right? That possibility should be there. Do we have that possibility? Yes, you have jump instructions, right? BUN, branch unconditionally. What do you mean by branch unconditionally? You can jump from first instruction to the 10th instruction if required. BUN. BSA, branch and save the return address. That is also equivalent to branch unconditionally only. Next, you can also skip the next instruction in the sequence. If the accumulator is based on the value of the accumulator, based on the positive value of the accumulator as well as the EBIT value. So based on those, you have skip instructions as well as branch instruction. Means you no need to follow the sequence which is given blindly. If required, you can also sequence. You can move from one place to the another place. You can jump from here to there. That is your jump. Then only you can control the program. So those type of instructions were also there in the 25 instruction. And the last one is you should have a communication with the IO devices. Means whatever is coming given by the input device, you should accept. In the same way, you should also present something onto the output device. You should have the instruction to perform these two things. Do we have that? Yes. In IO instructions, you have. Using this OUT and OUT and INP instruction, you can get the data from the input device. You can also produce or give the data onto the output device. So all these four conditions were satisfied. Therefore, I can say that my instruction set of instructions we have, and all these together, all these 25 instructions represents a complete set of instruction. Is it clear? Now, move on to the next slide. Move on to the next topic, timing and control. Timing and control. Okay. So, for controlling the system, you need to control the computer. You should control your computer, and it is given time, some given operations are to be performed, right? So timing is to be followed, and you should also control the system, right? So to perform this, you require a controlling unit. You require a controlling unit is designed using two methods. First one is hardware control, and the second one is microprogrammed control. Control unit can be designed in two ways, hardware and microprogram. Now, in case of hardware control, the control unit is implemented with the hardware components like logic gates, flip-flops, encoders, decoders, and so on, other digital circuits, right? So, the control unit is implemented with the hardware components in case of hardware control. Now, using this hardware control, if you want to perform any changes, how you will change? How you will get the changes? Just by changing the wiring between the hardware components, right? By changing the wiring in the hardware component, you can change the control unit. This is something like hardware, something like your hardware components you are using. And the second one is microprogrammed control. This is something like your software. So in microprogrammed control, all the control information is stored in the form of a program. Control information is stored in the form of a program, where in control memory. In the control memory, control information is stored, and this control information is in the form of a program which contains a set of micro operations. Program contains set of micro operations. For example, if I want to perform any addition operation, then what are the sequence of the micro operations to be executed? All that sequence will be stored in your control memory. Now, in case of hardware organization, if you want to do any changes where you are supposed to do the changes, you should change the wiring between the hardware devices. But here, you need to change the program written if you want to do any changes, right? Always software is program, right? So if you want to do any changes, you need to change your program in case of microprogrammed control. Now we'll see hardware control unit in this unit. In the second unit, we'll discuss about microprogrammed control. Let us see the hardware organization. How the control unit is designed using this hardware control, hardware organization. So what is required? This hardware control unit organization uses a sequence counter, decoders, and logic gates. Sequence counter, decoder, and a logic counter or logic gates. Why a sequence counter is required? Why sequence counter? Because everything in the computer is working on a time. Everything in the, we cannot work randomly. Based on the timing signals only, every instruction in our computer system will work. That is the reason you require a sequence counter, and here we are taking a 4-bit sequence counter, right? 4-bit sequence counter. And what are the 3 input signals given for this sequence counter are these: increment, clear, and clock. A clock cycle should be given. If required, you can clear the content of the sequence counter, and you can also perform increment. You can increment the sequence counter, right? Let us see the organization. So this is your control unit of your basic computer. You already know the format of your instruction, right? Instruction register always of size 16 bits. 0 to 11 bits are given for the address field. 12 to 14 bits are for opcode, and 15 bit is the your ith bit. Now you have a logic gate, and I am using a 4-bit sequence counter. Along with these two, we are using 2 decoders. One is 3 by 8 decoder. What is the difference between what is this decoder? In case of multiplexer, from multiple inputs you can get a single output. But in decoder, you are getting multiple outputs. More than number of inputs are less than the number of outputs. More inputs you will get in case of decoder. If the number of inputs are 3, number of outputs will be 2 power 3. 8 outputs you will get. In the same way, one more decoder you are using is 4 by 16. Number of input lines are 4. So how many output lines you will get? 2 power 4, which is 16. So the size is 4 by 16. Now we'll see. This is your 4-bit sequence counter. Means 4 input line. The input line of the sequence counter are given for the 4 by 16 decoder. The input lines of sequence counter are given to 4 by 16 decoder. So it will produce 16 timing signals. This decoder will produce 16, 0 to 15. Total of 16 timing signals from T0 to T15 are produced, and it is given to this logic gates, control logic gate. Next, 0 to 11 bits of the instruction register are directly given as input. Next, these opcode bits, how many are there? 3 opcode bits, 12 to 14 bits. These are given as a input to a 3 by 8 decoder. These are given as input to 3 by 8 decoder. Right? Now, this will produce 8 different output lines. This 3 by 8 decoder, using these 3 input lines, 8 different output lines were generated from D0 to D7. And the last 15th ith bit is also is directly given to this control logic gate. From this you will get a control output. Let us see one example. If the instruction is like this, if the instruction contains this data, your opcode value, 0 is the 15th ith bit, 001 is your opcode value, and these are the 11 bits, right? Now these 11 bits are directly given for the logic gates, right? When you see here, these 11 bits are directly given. You are not changing those 11 bits. Now you are taking the 3 bits of code given for the 3 by 8 decoder. Now in this example, what are the 3 bits in the opcode value? 0, 0, 1. So using these 3 bits, you will get 8 output lines, right? 8 output line. Now whenever the value is 0, 0, 1, 0, 0, 1, which output line is selected? The corresponding decimal value is 1. For 0, 0, 1, the corresponding decimal value is 1. So the D1, the first output line, whatever is connected to this first port, that first output line, which is D1, it is selected. And at the time of designing your computer only, at the time of designing the system only, these 8 bits are given with These 8 different lines are given with different operation. According to that, D1 is used for addition operation, right? So by seeing these three opcode bit value, we'll come to know that 001 is used for addition operation. Clear? So addition operation is performed. Now you need to know whether it is a direct or indirect. As the 15th, as this ith bit value is 0, so whatever the address value is present from 0 to 11 bits, that is your direct address. Means to perform this addition operation, you should go to this desired location. You should go to the location using this value. Go to this address location, fetch the data present at that location. Clear? In the last one, I'll wind up with this topic. Next, we'll see how to perform the timing cycles. Let us consider one register transfer language. You already know in the first class itself I explained how to write a register transfer language. P colon something. What is to be performed? What is the P? P is a control variable. In the first class I explained. P is a control variable. So control unit will generate the control variable. If the value of control variable is true, that means if it is 1, then whatever is written after colon, that will be executed. Here my P value is D3 T4. That means value of D3. Here I am just taking one example. I am taking one example. D3 value is equal to 1 and T4 should also be equal to 1. If both D3 and T4 are equal to 1, then what you are supposed to do? Make the sequence counter to 0. Let us see how the timing cycle will be for this particular register transfer language. Now we have different clock cycles. T0, this is T0, this is T1, next T2, T3, T4 and so on. These are the different clock cycles. Now T0 is activated. This is your T0 clock cycle, right? In this clock cycle, T0 will be high. T0 will be high. In the remaining time, it will be low only. That is, it will be 0. Next, T1 will be high from here to here. T1, high. Next, T2 will be high from here to here. So, T2 will be high. Next, what is the condition to be satisfied? T4 should be equal to 1. So, whenever T4 is 1, here in this region, in this clock cycle, T4 value is 1. At that time, if your D3 is also equal to 1, check if your D3 is where D3 value is 1. And my D3 value is 1 from the clock cycle T3. D3 is equal to 1 from the clock cycle. From here, third clock cycle, T3 will start. You just observe the clock cycle. This is T0 clock cycle. From here to here, T1, T2, ఒక్క నిమిషం, T3, right? So, D3 clock cycle, here it is 1 from this T3. T3 becomes 1 from this D3. But what is the condition to be satisfied? Both T4 and D3 should be equal to 1. In this region, they are 1. Whenever this condition is true, what are you supposed to do? Made the sequence counter to 0. So, here, made the sequence counter to 0. Now, your sequence counter is cleared. Next, generally, after this T4 clock cycle, you should get a T5 clock cycle. But what happens is, here at T4, you made your sequence counter as 0. So, the next clock cycle will start from T0. The next clock cycle will start from T0, not from T5. Why? Because you made the clock cycle. You made the sequence counter to 0. Right? This is about different computer instructions you have in your system. Is it clear? Actually, I thought of explaining this instruction cycle today itself, but there is no time. Okay, we'll see it in the next class. If you have any doubts, you can tell me. You can ask me in the chat box. Did you understand? Did you all understand? Any doubts? Let me know whether you understood or not. Someone is typing Durga Prakash. No doubts, ma? If you don't have any doubts, I didn't understand which P corresponds to which T. Can you? Okay. Durga Prakash. Okay, see this, ma. See this clock cycle. This is your clock cycle started from here. So, what is the first 0? Next, T1, T2, T3, so on. Right? So, this is your T0, right? So, T0 is high or T0 is equal to in this region. Next clock cycle, T1, when it will be 1 in T1. From here to here, it is T1, right? So, T1 is high. Next, in the next cycle, T2 is high. In the next cycle, T3 is high. In the next, T4 is high. Only here T4 is high. Next, in the remaining clock cycles, T4 is 0. Another clock cycle may be 1. Now, condition is what? T4 should be equal to 1. D3 should also be equal to 1. Check when D3 is 1. Right? So, the value of D3 is 1. And this is, I'm just considering this example, ma. You cannot say that D3 is 1 starting from this T3 cycle to T4. You cannot say that. Based on the type of instruction, based on the program we are executing, D3 may be high at one clock cycle. Here I am considering that D3 is high in T3 cycle, T4 cycle and so on. Starting from T3 cycle, my D3 is high or my D3 value is 1. Now condition is what? Both should be true. Only in this region, both are 1. What are you supposed to do? You should make the sequence counter to 0. So clear the sequence counter. When? Here. Clear the sequence counter. When you clear the sequence counter, the next clock cycle, that means you are starting from the initial clock cycle. So again start with the clock cycle as from T0, T1 and so on. So the clock cycle again started from T0. Is it clear? Durga Prakash did the recording, ma. Obaid Ullah KMIT, Sheikh Obaid. I'll send the recordings. Any other doubts? Shall we start the quiz? Okay, thank you. I'm going to start the quiz, ma.